we're going to get into the idea of scattering and how we think about that in this with what we've been doing. But first, a really quick recap of what we've been doing these last few videos. We've been discussing things in the position representation, where our state kets are represented by these wave functions in position space, and our energy eigenvalue equation that we use to sort of solve for what those wave functions are is mapped in position space to this. And this gives us sort of the differential equation we use to solve for our energy eigenstates given a potential. What we looked at was we looked at bound states where the energy of the state was less than the height of some barrier in the well. And because that energy was less than that well, we have these boundary conditions where the wave function has to be continuous, as does its derivative, and that quantized the possible energy states. Those boundary conditions imposed restrictions on that wave vector k that made that quantized these states. So for the finite square well, this is what we were looking at. In the last more recent lectures, we went into looking at free particles where we didn't have this well here. We just had particles free to move everywhere. And we saw that without those boundary conditions, we actually had a continuous spectrum. The particle could take on essentially any energy value. And the wave functions ended up being these wave packets, the eigenstates in momentum space. And we had the idea of these momentum space wave functions as well as the position space wave functions. And they were the Fourier and inverse Fourier transforms of each other. But it was basically you formed a wave packet that would localize a particle in space at the cost of sort of a distribution of momentum that it could have. And we got this sort of the Heisenberg uncertainty principle, where essentially if you localized the particle more in space, you had more of an uncertainty or a spread in the momentum eigenstates that made it up, and vice versa. What we're going to do today is we're going to consider particles that have an energy larger than a well. We are going to consider potential wells, but the energy state or the energy of that particle is going to be greater than the depth of that well. So it's still free to run off to infinity in either direction. So typically this sort of analysis is what we use to look at what are called scattering experiments. So if you have a typical scattering experiment, we have some source of particles that we control, and we give those particles a given energy and fire them at some target, typically, another particle or something, say. And those particles are going to have an interaction. They're going to have maybe an attractive interaction between them. And if you recall that, there's going to be a potential energy associated with that interaction, right? And you can model that potential a bunch of different ways. The way we're going to do it today is we're going to just use a finite square well as a model of the interaction, right? So we're looking at trying to figure out the eigenstates, I guess, of what's going on with the particle we shoot at this target, and the potential it experiences is just this potential, this finite square well, is how we're going to model that target. One of the things I want to note is we are free to set what our zero is for potential energy. This is something hopefully you recall from intro physics, in that we're not really concerned with the absolute value of potential energies, more of changes in them. So what's typically the convention is that you set the potential energy at infinity to zero, and then the wells go below zero, and barriers and other things go above. So that, in this case, our square well potential looks like this, where it's zero outside of the well if x is less than negative a or x is greater than a. And inside the well, that potential energy goes down to negative V0. So this also means that bound states have energies less than zero, and these sort of free states will have energies greater than zero. And that's what we're going to look at. We're going to be looking at energies at situations where the particle energy is greater than the depth of that well. And our goal is, again, we're going to look at the energy eigenvalue equation and try to solve that and figure out, everything we can about, the scattering experiment, so to speak. So hopefully we're kind of familiar with how to do this. If we look at the outside of the well area, so x less than negative a or greater than a, our energy eigenvalue equation looks like this. We've done this a bunch of times before. You can rewrite this differential equation as just the second derivative of our eigenstate is equal to some wave negative of some wave vector squared times our eigenstate again. And in this case, our k1 is just 2me over h bar squared, all square rooted. For inside the well region, we have a very similar situation, except for instead of 0 here, we have that negative V0 potential energy. Again, though, the differential equation can be written the same way. It's just our wave vectors slightly different. This time it has E plus V naught there instead of just the E. We've seen these differential equations before. We know the solutions to them. We've been going over them for a few weeks now. There's two ways to generally write these solutions that we've talked about: sines and cosines versus exponentials. You know, we're looking at the case where energy is above the potential well depth. So we're not looking at bound states. We're looking at essentially waves traveling. So we're going to use the exponential versions of these. So those solutions end up being this. In region one, over here, where x is less than negative a, we just have, you know, wave traveling to the right and wave traveling to the left, both with wave vector magnitude k1. Inside the well region, we have the same sort of thing, wave traveling to the left and right, with wave vector k2. And then on the other side of the well, we have, you know, the same solution. And you can take the derivatives of these and show that you end up with negative k squared times that original function. But we've done this, so hopefully you're comfortable with us just moving on from there. We also have the boundary conditions. This is typically how we went about solving for that. We need to know A, B, C, D, F, and G here, as well as the energy that goes into K1 and K2 here. And we have four equations from the boundary conditions. One, that the wave function has to be continuous at negative A. One, that it has to be continuous at A. And then likewise, the derivative of that wave function has to be continuous at both of those things. That gives us 7 unknowns, all those coefficients, and as well as the energy. And we only have 4 equations right now. Normalization would be another set of equations that we could use to help get at this. But if we think a little more carefully about a typical scattering experiment and what we have access to and what we know or can know, we can simplify our lives a bit, right? Remember, the experiment is I have control over a particle going to the right. So essentially, I control this term here, a e to the I kx1. That's a wave traveling to the right in this region. That's what I'm, you know, kind of setting in my experiment. And what I'm concerned with is I can measure, you know, if the particle bounced back, if it got through. I don't really have access to, you know, what it was doing in, you know, when it was interacting with the particle before that. So I'm really most concerned with A, B, F, and G over here. And if you also think about it, if it gets past the well, there's nothing that's going to reflect it back. So there's no there's no wave over here traveling to the left. So I can essentially just say right away that that G is going to be equal to 0, and that we're mostly interested in just the amplitudes B and F. You know, I control A, B and F are the reflected amplitude, F is the transmitted amplitude, and I don't really have access to C and D, so I don't need to solve all of these to really get a lot of useful information. And that's what we're going to go through today. The boundary conditions, the two boundary conditions at negative A give us the wave function has to be continuous. So the wave function in region 1 and region 2 have to be equal. If I plug in negative A there, I get this equation. If I take the derivative of those two, the wave function in region 1 and 2, and then plug in negative A, I get this equation. And then if I do the same thing for regions 2 and 3, and plug in the value of A here, I get these two equations. So we have these four sets of equations, and what we're trying to do is essentially get information of B, and F in terms of A, what we know. So we can use these equations essentially to get rid of the coefficients C and D. There is a ton of algebra in that in here. So I'm not going to go through all the details, but the gist is these first two equations, right? If you essentially solve for C and D in terms of F, we get these two equations here, right? So that, it's tedious, but worthwhile doing. We get these two equations. Then if I do the similar sort of thing with those two, I can get A and B in terms of C and D. And then if I substitute these C and Ds in for those, I've essentially eliminated C and D from this system of equations, and I've got A, B, and F are my unknowns in these things. So again, make those substitutions, and do a bunch more algebra, and we end up with these. Again, I'm not going through all the details of this algebra. You can pause the video and do the steps in between. I may even ask for it on a homework, but this is what we get up. And then the last thing we want to do is remember we're controlling A, the amplitude, how much, essentially the particle flux that we're sending at that target. So we want to know essentially the ratio of F to A and B to A, because those are going to relate to how much is reflected or transmitted. So if we take those ratios, again, a bunch of tedious algebra in that, but we get these two equations for the ratio of F to A and B to A, right? And the squares of these are essentially the probability that a particle's going to be reflected or transmitted, right? We have, A squared is sort of the amplitude of the incoming wave, or the probability amplitude of the incoming wave, and B squared and F squared are the reflected and transmitted parts of those. So we can define these transmission and reflection coefficients, T and R, as the squared amplitudes of those coefficients, right? And when you do all that algebra, it comes out like this, right? So again, not going through the detailed algebra, pause the video, check the steps in between, and make sure you can get there. But an interesting, so T is essentially the probability that that particle is transmitted through the target to the other side, and R is the probability it is reflected. And what you'll notice is there are resonances here where this sine squared term will be equal to 1, or will be equal to 0 rather, and the transmission probability is unity, that the particle will with 100% probability get through that target. We can actually think of that in terms of energy if we make the substitutions for what our wave vectors were in terms of energy. And when we do that, we get this equation here. And you can notice a lot that kind of intuitively would make sense here. The first thing is if I make that well deeper and deeper, so I increase the size, the depth of that interaction potential, that's essentially going to make this V naught quite large, which is going to make the denominator much larger, and the probability of that particle getting transmitted through or getting through the target starts to go down and down and down. Whereas if I, make that potential less and less and less, it's less likely to cause some scattering in that. But back to these resonances, right? If you plot that energy, in units of the potential well depth, you're seeing that there at certain energies, this sine term goes to 0, and the transmission probability is unity, right? So there are certain energies where if you shoot that, say the particle at your target, at certain energies, they will have resonances where they will definitely transmit through to the other side. And if we want to analyze when that occurs, it's simply when this sine term here goes to 0. So it's when sine 2k 2, so that's the wave vector in the region where the well is, A is equal to 0, right? Which occurs when the argument of sine is equal to some integer multiple of pi, right? Um, and we can take this a little step further and acknowledge that K2 can be written in terms of the wavelength of that particle in that well region, so lambda 2, and we can sort of see when those resonances occur. Now, if you think of what our well went from negative A to plus A, so this 2A is just the length of our well, or the size in space of our well. So if we solve for that wavelength, these resonances occur when the wavelength lines up with a half, essentially, when it's commensurate with the width of that well, right? So this is quite similar to thin film interference that you may have covered in previous courses, where if you have just light coming through a thin film of, say, glass, or a typical example is soap bubbles, and you get multiple reflections inside that thin film, you can get resonances where the path length traveled by all the waves going one way interfere constructively, and all the waves going the other way interfere destructively, and all the light travels through, and you get these peaks in transmission. It's a similar type effect here, where at certain energies, you will, which will determine the wavelength of that particle, you'll get resonances with 100% probability of transmission. So that's essentially it for today. We kind of went really quick through that. Most of it is a lot of algebra to sort out what those coefficients are, and solving, eliminating C and D from our boundary condition equations to solve for that. But the process we went through is very similar. We start with just our energy eigenvalue equation, and imposing boundary conditions uh, on what the solutions to that are to solve for our unknowns. A cool thing, or an interesting thing, I suppose, about having done this is we did this for a well, an attractive potential between some particle. It would also work if that potential was positive, if it was a barrier, if there was an interaction that repelled the particles away. All the math is identical, except, and you still would get resonances and everything, except for it only works if that energy is still greater than this potential height. The difference also would be the wavelength in this region would then be longer, because there'd be less kinetic energy, so there'd be less curvature. So this condition, it would change the spacing between resonances and that, but essentially the physics is going to be all the same, and you can follow the exact same process to get the exact same transmission and reflection coefficients for a finite square well or a finite square barrier. Um, what happens when that energy is less than that potential barrier leads to the effect known as tunneling, which is going to be the subject of our next video. So as usual, if you have any questions, feel free to reach out to me, and I will see you in our synchronous sessions.